Hey everyone, grab your virtual hard hats, because today we're building robots. But here's the catch, we're not going to touch a single piece of hardware. We're diving into the amazing world of robot simulation, where we can test a wildly complex robot in a bustling virtual hotel, and honestly, not break a single plate or spend a dime. Let's see how we bridge that gap from abstract code to actual mechanical movement. So here's the big dilemma in robotics development. You've got this awesome design, right? But how do you actually test it before building the physical thing? Imagine dropping thousands of dollars and months of sweat wiring up a prototype, turning it on, and just watching it instantly crash into a brick wall. Yeah, nobody wants that. That insane physical and financial risk is exactly why we need a virtual sandbox. To get us there, here is our roadmap for this explainer. We'll quickly look at why we simulate, dive into the math of movement, cover the basics of the robot operating system, check out the Gazebo simulator, build our virtual ChefBot, and finally, let it navigate a hotel totally autonomously. All right, kicking things off. Why do we even bother simulating? And what are the pros and cons of virtual prototyping? It's all a fascinating trade-off, really. On the plus side, you get zero hardware costs. You can tweak a design in seconds and run risk-free stage-by-stage testing. It's like having infinite redos. But there's always a catch, right? The downside is that a simulator can't perfectly mimic every tiny real-world detail. Unpredictable floor friction, a wheel that's just a tiny bit warped, super hard to replicate. Basically, your simulation only knows exactly what you program it to know. Now, to build these virtual worlds, the industry relies on a few heavy hitters. You've got tools like VREP and WeBots, which are amazing for 3D service and industrial bots. Then there's Robotics, which is super specialized for big 5-axis industrial arms. But for our purposes today, we're focusing completely on Gazebo. Why? Simple. It plays incredibly well with the robot operating system, which is absolutely the gold standard out there. Moving right along to the math of movement, let's talk about robot kinematics. Look, before we can play in our virtual sandbox, we've got to set up the rules of physics. We start by stripping away the dynamics, things like gravity, friction, and motor torque, and we just look at kinematics. This is the pure, unadulterated geometry of movement. It's entirely about figuring out exactly where the robot is and how its parts relate to each other in space. Let's ground this with something you probably have at home, like a Roomba. How does it steer? Well, it uses what we call a non-holonomic system. That's just a really fancy way of saying its movement is constrained. Think about your car. It's non-holonomic too. You can't just magically slide sideways into a parallel parking spot, right? You have to pull forward, turn the wheel, back up. You have to obey the geometry. To pinpoint our robot in 3D space, we track its 6 degrees of freedom. First, you've got position, simply X, Y, and Z. Then you have its attitude, roll, pitch, and yaw. Try this with your hand right now. Hold it flat. Tilting it side to side, that's roll. Pointing your fingers up or down, pitch. And spinning it left and right like a compass, that is your yaw, which is basically the direction your robot is heading. And this brings us to a super cool concept for differential drives, the ICC, or Instantaneous Center of Curvature. Imagine you're pushing a heavy shopping cart at the grocery store. To turn it, you pull back on one side and push forward on the other. Notice how the cart spins around this invisible dot right between the back wheels? That dot is the ICC. By doing some quick math on how fast the left wheel is spinning versus the right wheel, we can plot exactly where our robot is going to end up. Okay, let's give our machine a brain. Welcome to Robot Operating System Basics. Meet ROS. Now, despite the name, it isn't actually a traditional operating system like Windows or Mac OS. It's a meta operating system that basically piggybacks on your existing OS, usually Ubuntu Linux. You can think of ROS as the ultimate project manager. It provides a distributed framework that lets chunks of code written in totally different languages and running on completely different computers all talk to each other seamlessly. The way ROS handles all this chatter is brilliant. It uses a ROS master that acts just like an old-timey switchboard operator, plugging different nodes into each other. If a node is pumping out a continuous stream of data, say a live camera feed, it uses Topics. It's a publish and subscribe system, kind of like a radio broadcast where anyone can tune in. But if a node just needs a quick, specific action done, it uses services. That is a direct one-to-one request and reply. Now that we have a brain, we need a world. Enter the Gazebo simulator. Gazebo is literally our virtual physics playground. It uses hardcore physics engines like Odeo or Bullet to simulate dynamic movement. It gives us awesome 3D graphics, And the best part? The crazy rich sensor support. You can bolt a virtual laser scanner or a 3D camera onto your digital robot, and Gazebo will feed perfectly simulated realistic sensor data right back into your ROS brain. It doesn't even know it's not real. All right, time for the fun part. Let's actually simulate our custom service robot, the ChefBot. To drop ChefBot into Gazebo, we can't just wish it into existence. We have to hand this simulator a highly detailed blueprint. In the ROS world, we use URDF, the Unified Robot Description Format. It's an XML file that spells out everything. What does the robot look like visually? How do its joints bend based on that kinematics math we did earlier? And crucially, where are its invisible collision boundaries so it actually bumps into tables instead of phasing right through them like a ghost? We usually use a handy tool called Acro to write these files out efficiently. Getting this software ready requires a pretty strict routine. You don't just toss files into a random folder. We use the Catkin build system. You set up a dedicated workspace, create your specific ChefBot package, write up your publisher and subscriber nodes, and then boom, you run a single command, catkin_make. That compiles everything into executables that ROS can actually run. Let's put it all together. Here is how we get to autonomous hotel navigation. The workflow here is going to blow your mind. First, we load up Gazebo with a 3D hotel layout. But get this, ChefBot has no idea what this place looks like yet, so we fire up a process called SLAM, which stands for Simultaneous Localization and Mapping. We literally drive the robot around the hotel with our keyboard like a video game. While we drive, its virtual sensors scan the walls and draw a 2D floor plan in real time. Once that map is perfect, we save it, turn off SLAM, and switch on AMCL. Now the robot can look at that map, figure out exactly where it is, and navigate the hotel 100% on its own. Wow. Okay, let's take a quick breath and recap what we've covered in this explainer. Bridging the gap from mechanical design to software is no small feat. We saw that simulation saves us massive hardware costs and time. We learned how kinematics gives us the math behind the movement. We saw ROS acting as our brilliant switchboard, Gazebo giving us a world with real physics, and URDF acting as our master 3D blueprint tying it all together. Before we wrap up, I've got a quick pop quiz for you to test your memory. Based on what we just ran through, what are Gmapping and AMCL specifically used for? Think about it. Because the ability to map an unknown room and firmly localize inside it completely flips the script for robotics. If a machine can do that without us holding its hand, the applications extend way beyond serving food in virtual hotels. We're talking about navigating disaster zones, exploring deep space, or maybe just folding laundry in your living room. Keep learning, keep experimenting, and I'll catch you in the next explainer.